Jonas for the introduction. And Marcus and Jonas for organizing this and inviting me. Yeah, so I'll tell you about a recent work from a few months ago with Jonas Hafferkamp and Robert Walker. And because I know the audience is a mix of extreme experts on random unitaries and people who maybe don't work on this every day, I'll start with a kind of like high level introduction, but then by the middle of the talk, I'll get to kind of the full details of how we show everything. Okay, so starting zoomed way out. So at least for me, the motivation for all of this and all of these topics we think about is the tremendous progress in modern quantum experiments, which are increasingly able to reach very large numbers of qubits in very high degrees of coherence that are pushing the traditional regimes of study in quantum physics and information and computation. And this raises lots of interesting questions, like how do we benchmark a large quantum device? You know, maybe I've prepared some state. How do I verify that I've prepared the state I meant to prepare? How do large quantum circuits and Hamiltonians behave? How can we find quantum advantages, especially in near-term quantum experiments? And a question that will be especially relevant for this talk, what properties of quantum states and quantum dynamics are easy to measure in quantum experiments, and what properties are just fundamentally hard? And so in all of these questions, there's been a surprisingly ubiquitous tool that has helped us make progress. And this is the notion of a Haar random unitary. So a random unitary on n qubits is just a random 2 to the n by 2 to the n matrix drawn from the Haar measure on the unitary group. And if you haven't worked with these before, your first thought might be, why should I ever care about a Haar random unitary? Aren't I normally interested in some highly structured quantum circuit that does some computation that I want the result of? Or maybe some specific Hamiltonian that models some spins and electrons in the real world? And that's fair. But nonetheless, people have come up with lots of different reasons in very different areas of quantum information and physics to care about these objects. And I'd like to just briefly kind of zoom through a few of these reasons to give you a flavor of why different communities of people care about this. And I'll group these reasons to care about random unitaries into several classes. And the first class is random unitaries as an application. So instances where I actually want to apply a random unitary in a quantum device. And I think one of the most surprising applications comes from this paper a few years ago on classical shadow tomography, where they use random unitaries for fidelity estimation. And the basic protocol is as follows. So say I have some quantum system I've prepared in my experiment, and I want to estimate its fidelity with some target state. Well, their protocol proceeds as shown here. I take my quantum state, I evolve it under a random unitary, in this case, a random Clifford unitary, and then I measure in the computational basis. And then I do this again with a new random unitary, and I do it again with a new random unitary. And they show that after a surprisingly small number of times, this protocol allows you to estimate the fidelity of your quantum state with respect to any target state you so choose. So this is a kind of surprising instance where applying a random unitary really can lead to large advantages in certain scenarios. Another application, a case where we actually want to apply a random unitary, is in quantum supremacy experiments, such as random circuit sampling. And in particular, some of our best arguments for why random circuit sampling is classically hard rely on the resemblance of random circuits to random unitaries in the form of this property called anti-concentration. And a third application, which is more of a potential application that some people have been thinking about, is in quantum cryptography. So it's known that random unitaries are very good at hiding information. There's been at least lots of excitement that this might be useful in quantum cryptography. Okay, so a second class of reasons why we care about random unitaries is not because we actually want to apply them, but we want to use them as a toy model to help understand the systems that we actually do realize in the physical world. So this has been a tremendously successful line of research in quantum many-body physics and many-body dynamics over the last decade. It's also been very useful in quantum machine learning, understanding challenges in training variational quantum circuits and machine learning models. And it's also been actually a really widespread tool in our modern understanding of the ADS-CFT correspondence as well. And this brings me to kind of my final reason for caring about random unitaries, which is as a counterexample. And so this harkens back to this question I asked on the first slide: what properties of a quantum state are easy to measure and what are hard? And it turns out that random unitaries are probably our best theoretical tool for proving that certain properties of quantum states are just fundamentally hard to measure. The strategy is essentially to take a random state that has the property of interest and to show that learning something about that random state is very hard. And so this has been at the heart of a lot of recent progress in quantum learning and establishing advantages in quantum learning. And so in all of these different motivations, there's one question that is very important, which is in what circuit depth can a random unitary be generated? So this is clearly important if we actually want to apply a random unitary. It tells us how many gates we need to apply. But it's also important if we're thinking of these as a toy model or a counterexample. It tells us when this analogy between what's happening in the real world and my random unitary kicks in. Is it only at very late times or very large depths? Or is it maybe at shallower depths, shorter times? And if you just initially think about this question, the answer seems to be rather pessimistic. So a truly hard random unitary with very high probability has exponential depth. There's simply many more deep circuits than shallow circuits. So if you choose a random circuit, it's very likely to be deep. And what this tells us is that any useful answer to this question requires some notion of approximation. So maybe an ensemble of quantum circuits is not precisely equal to the Haar random ensemble, but it looks like the Haar ensemble. It's indistinguishable from the Haar ensemble for some set of experiments or applications I'm interested in. And so with this broad idea in mind, people have defined kind of two different notions of when an ensemble of unitaries looks Haar random. And we'll deal with both of these in this talk. So the first notion is that of a unitary K design. And so informally speaking, an ensemble of unitaries is a unitary K design if it's indistinguishable from a Haar random unitary in any experiment that queries you K times. And so by any experiment, I really mean any experiment. So an observer prepares an arbitrary initial quantum state, applies U, does an arbitrary quantum operation or POBM after that, then applies U again, then does an arbitrary quantum circuit or POBM, then applies U again, so on, K times. And for the experts in the audience throughout this talk, I'll be considering K designs defined with respect to the relative error. So the relative error is defined as follows. I consider the channel where I take my unitary K times in parallel and I apply it to a quantum state. And then I demand that this channel for my ensemble of unitaries is very close to the channel for the Haar ensemble to within a multiplicative error epsilon. So this is often called the relative or multiplicative error, and it's a very strong notion of error. It's stronger than other notions based on like diamond norm or Schatten P norm, etc.
Why do you consider here parallel instead of like that's
Great. Yes, so the reason is this error is in fact so strong that I can show you at the end. But it's so strong that I can basically apply it to show that even when we apply them in sequence, if it has this relative error, then it's indistinguishable when I apply in sequence. If we used one of these weaker notions of error, like the diamond norm, this statement would not hold, and it would be very important that this was in parallel, not sequence. But there's a kind of cute trick for moving between the two. Cool. And yeah, please just interrupt with questions every time. Okay, so that's a unitary K design. Much more recently, people have introduced another notion of random unitary called a pseudo-random unitary. This is kind of a computational version of a K-design. And so the definition of a pseudo-random unitary is that a random U chosen from my ensemble is indistinguishable from a Haar random unitary in any efficient quantum experiment. And here, efficient means, first of all, that I can query U any polynomial number of times. So polynomial in the number of qubits n. So this might be many, many times, K being any polynomial in n. And so that seems a bit stronger than just this unitary K design. And so in exchange for that, I weaken the type of circuits I consider a little bit. I demand that it's only just indistinguishable from a Haar unitary in efficient experiments. So where these quantum circuits have polynomial depth. So K designs resemble Haar for arbitrary quantum circuits in between. Pseudo-random unitaries demand that these circuits have polynomial depth. And typically when proving properties of pseudo-random states and unitaries, we have to make some assumption about the computational power of polynomial depth quantum circuits. And so we normally prove that something is pseudo-random under some standard quadratic assumption about how powerful quantum circuits are. Yeah.
For K in the K design? Oh, maybe I'm about to get.
Okay, yeah.
Okay, I'll wait, yeah.
Okay. Yeah, before introducing our results, I'd just like to review what people have already discovered about these objects. And so I'll start with unitary K designs. So for unitary K designs, our best results on K designs come from this long line of research on random quantum circuits. So say I arrange my qubits on a 1D line, and at each time step, I apply a random 2-qubit gate to every nearest neighbor pair of qubits. And I do this with new random gates at every point in time. And so a long line of works, including some quite nice recent ones by Jonas, have culminated in showing that local random circuits form K designs in depth K times n plus K times log 1 over epsilon. So epsilon here is a notion of approximation error. And this is quite remarkable, namely that this depth is only linear in n, because we knew that a true Haar random unitary required exponential depth. But now these, just linear depth quantum circuits are just as good as Haar random unitaries in any experiment that queries them K times. So for pseudo-random unitaries, our progress has been much, much more recent. And in particular, this recent work from a month or two ago by Fermi-Ma and Robert Huang proved the existence of pseudo-random unitaries. So they provide the first proof that pseudo-random unitaries exist. And they proved this for an ensemble of circuits called the PFC ensemble, introduced in this earlier paper by Medgar et al. So just to briefly tell you what the PFC ensemble is, it's not super important for my talk, but just to give you some background. So this C is a random Clifford on all n qubits. This F is a random phase gate on all qubits. So for every computational basis state, I apply a random phase, a random plus or minus 1 to that computational basis state. To be precise, this phase is chosen to be pseudo-random, which is some notion that under any polynomial time quantum experiment, it's indistinguishable from a truly random phase. And this P is a permutation on all of my computational basis states. So it shuffles all of my 2 to the n computational basis states in some random way. And again, like F, it's actually pseudo-random, but it's indistinguishable from truly random. So this is the construction. People call it the PFC construction. And Fermi-Ma and Robert Huang proved that this construction is a pseudo-random unitary. And if you take this P and this F and this C and you compile them as some product of local gates, you get that pseudo-random unitaries can be generated in depth poly n in 1D circuits and poly log n in all-to-all circuits. So in 1D circuits, it's kind of a similar scaling with n compared to these K designs, both polynomial and n. And for this PFC ensemble, you can also do a bit better if you leverage really non-local connectivity. And so before moving to our results, I'd like to just remark that at least I and many people thought these circuit depths seemed really reasonable. So for example, 1D circuits require linear depth to generate high entanglement across any cut, which is certainly a property of Haar random unitaries. And they also require linear depth to have extensive light cones, which touch all the qubits in the system. And by very similar arguments, one can easily show that classical circuits require linear depth in order to be pseudo-random or to form designs in 1D. And the argument is super simple. So you take some classical circuit and you apply it to two different input states. So you query the circuit just twice. And you choose these input states so they only differ in one bit, say the first bit of the system. And then you just look at what you get out. And if you did a not Haar random, but if you did a random classical circuit, you would get out two completely random bit strings, which have no correlation with each other. But if you do a very low depth circuit, a very basic light cone argument shows that all of the bits that are far away from the first bit have to be the same. So you just query it twice, you see if all these bits far away are the same, and then you know whether your circuit was low depth or whether it was random. So today I'll show you that something very different happens in quantum circuits. So just to state our results, our first result is that random quantum circuits in 1D can form unitary K designs in depth K times log M in 1D or any circuit geometry. So this is the same K and epsilon dependence as before, but an exponentially improved N dependence, where N is the number of qubits. And our second result is that quantum circuits can form pseudo-random unitaries in depth poly log n in 1D circuits and poly log n in all-to-all connected circuits. So these circuit depths are very small. There's a joke, I think that log n is less than 5. And so just like a broad remark, these circuits are very shallow. They have very low complexity and they create only very local short range entanglement. And yet our results show that they're indistinguishable from random unitaries with exponential complexity. And so I want to first give some intuition, like why this is possible, why we should not be that surprised in retrospect that this is true. And then I'll go into the details of what our construction is and how we show this. Yeah.
So for the K design, is it only apply if K is constant, or can you allow K to be growing with N to some extent? Does it depend on like
Our results.
error kind of?
Our results apply for any K, but the depth is linear in K,
Yeah.
always.
So I was
So
wondering, is it like so I guess there's also some approximation factor you're hiding, which I would assume depends on K as well. Or?
yes, I think I have to think about this, but I'll get to it. But yes, there will be some restriction on K, although it's a little bit tunable. So if you want larger K, you could. But the main advantage comes for constant K.
Yeah.
I'll get to the details though. Okay, so to start with the intuition. So why does this simple argument for classical circuits requiring large depth not hold in the quantum case? The basic intuition is that unlike classical circuits, quantum circuits can locally hide information into non-commuting observables. And so let's walk through classical and quantum just a little bit more step by step. So what does a classical circuit do, or a classical experiment do? So I prepare some local information. I prepare a bunch of bits in the 0 or 1 state. And then I apply my circuit. And when I apply my circuit, this local information about each bit is spread into slightly more non-local information acting on Xi bit observables, where Xi is the depth of the circuit. And then at the end, I measure all my qubits in the Z basis because it's classical. And the crucial thing is that because the circuit is classical as well, my information is spread into Xi bit classical observables. So these observables are always in the Z basis. And what that means is that these observables always affect my measurement results. this is kind of obvious because this is a deterministic, a reversible classical circuit. And what this means, you know, in practice in this example is that I can always tell if this first bit is flipped by looking at, you know, whether my outputs are different. And I can always tell that all of these bits were not flipped because my outputs will always be the same. So this might sound obvious, but let's now look at what happens in the quantum case. So a quantum experiment is very similar. I prepare, say, some local information, a bunch of qubits, say in the computational basis even. And then I apply my quantum circuit. And when I do that, the local information about each qubit is delocalized into Xi qubit observables. And then at the end, I measure my circuit in some basis that I choose. And the key difference is that my information is spread into qubit observables, which might not commute with each other. And in particular, they might not commute with my choice of measurement basis. And if I delocalize some information into an observable that doesn't commute with my measurement basis, that information is invisible to my measurement results. So if I put some information into a coherence, into, you know, some observable with an X somewhere, and I measure in the Z basis, this information never affects my measurement results. I get just pure randomness instead. And the key observation is a random Xi qubit observable is very, very likely not to commute with any fixed measurement basis. It's exponentially unlikely in Xi because there's exponentially many Pauli observables on Xi bits, and these largely don't commute with one another. And so if you try to run this kind of light cone argument with a quantum circuit, you'll find no matter what you do, it simply doesn't work. It always runs into some exponential barrier in the depth Xi. And the basic reason why is just you don't know what basis to measure. So that's just the kind of rough intuition for why this is not so surprising in retrospect.
Sorry, but in the classical case, what if you had like an array of random single Pauli measurements at the very end?
Mhm.
Would you then be, would it be still like, would you still need to?
You mean like random
Yeah, just
Pauli rotations
yeah.
at the end of the classical circuit? I don't know. Maybe it feels like it shouldn't work, but my argument certainly breaks down. Maybe there's some smart thing you can do because it has more structure.
You're sort of halfway to constructing a PFC ensemble, like doing a P and then a bunch of random single qubit Cliffords. And then you'll find that you need to like do some, get some more coherence out. So you'll do a whole Clifford and then you're basically there.
Good question. Okay, so what are the circuits we construct? So our approach, I call it building a random unitary brick by brick. And it's a rather general approach, which allows us to exponentially reduce the circuit depth of lots of different constructions of random unitaries. And so our construction is shown here on the left. We basically take all our qubits, we lay them out on a 1D line, and we group them into patches of Pauli log n qubits each. And then our circuit is just a 2-layer circuit. In the first layer, we take the first patch and we apply a small random unitary on Pauli log n qubits to it. And then we do the same for the second patch and the third patch and so on. That's the first layer. And then we do the same thing in the second layer, just shift it over by half a patch to form this brickwork pattern. And that's the whole ensemble. Each of these unitaries is independently random on Pauli log n qubits. And we show that this ensemble is indistinguishable from a Haar random unitary. So in more detail, so we provide 2 theorems, one for K designs, one for pseudo-random unitaries. For K designs, we show that if each small random unitary is drawn from an epsilon over n approximate K design on log nk over epsilon qubits, then the whole circuit forms an epsilon approximate K design on all n qubits. So you can think for K designs, each of these individual unitaries is drawn from like a local random circuit on log n qubits. And we know that we can realize K designs on, log n qubits in K times log n depth. So we know it takes linear depth in the number of qubits. So if the number of qubits is log n, then the depth is log n. And so the depth of each small unitary is like K log n. And this means that the depth of our circuit is 2 times K log n. So we've basically doubled the depth, but now our design acts on exponentially more qubits. You'll also notice if you look at the theorem that we require each small random unitary to have a relatively good error. So we require like epsilon over n approximation error for each small unitary. This is basically because we need to add up errors from every small unitary and we need the total error to still be small. But this is pretty innocuous because our scaling of the error with epsilon is already very good. It's already log 1 over epsilon. And so making epsilon 1 over n just leads to, some log n overhead, which is fine for us. So this is our result on unitary designs. Yeah.
Well, why do you know that quality on the right is true? So is this kind of.
This is these previous results on local random circuits. So
It's also recent or?
So there's a long line of works. This is the result I'm referring to, the 1D random circuits from K designs, and this was shown in 2012 by Brando, Harrow, and Hordecki, and then the K dependence has been improved in many more recent works.
So we're relying.
Yeah. So we are, the reason I mentioned these two results is we're going to rely on both this and the construction of periods. Yeah. So we don't really, we bootstrap lots of existing results, and our core technique is just kind of inserting these results in small patches to get a random unitary on all of the qubits. Okay. And so I'll just also state our result on pseudo-random unitaries. So if each small unitary is drawn from a PRU, a pseudo-random unitary, on polylog n qubits, so slightly more qubits now, then we show that the whole circuit forms a PRU on all n qubits. So very similar to before. And again, we can think of each small unitary as being drawn from the PFC ensemble on some polylog n number of qubits. And so in 1D, we know the PFC ensemble can be realized in poly n depth. That means that our circuit can be realized in polylog n depth, because each patch is only polylog n. And for an all-to-all connected circuit, we can realize the PFC ensemble in polylog n depth. So if we take n to be polylog n, then we can realize a pseudo-random unitary in polylog log n depth. And just a brief comment. So you saw before on the designs that our approximation error got slightly, we were required to put in a very good approximation error, and we got out a slightly worse one. And something kind of similar happens for the PRUs. So we have to require each small PRU to be secure against poly n times adversaries. And I'm going to write this in a funny way. It's kind of, so n is the total number of qubits. So this is sub-exponential security with respect to polylog n qubits. This is a detailed point, so don't worry about it if you don't want to. But basically, we need to put in some relatively good ensemble of pseudo-random unitaries with sub-exponential security. And what we get out is a pseudo-random unitary ensemble with polynomial security. So it's again a similar spirit. You put in something very good, you might get out something slightly worse. But I do want to say this is kind of we can show this is optimal, and it's also very tunable. If we make these patches bigger and bigger, we can kind of continuously interpolate between the PFC result, which has sub-exponential security, and get lower and lower depth results with slightly less and less security. So it's both necessary that it gets slightly worse, and it's very tunable. Yeah.
I ask a very simple question, but do these like log n acting qubits random unitaries exist? Like, is there not some moment where they stop existing? So that the tomography and learn them?
Wait, sorry, what was the question? That polylog n might be too small, or?
I don't know, what's like the smallest unitary you can consider such that you cannot just
Mm.
learn them and they're not random. Like that.
Yeah, I think, well, I guess we're always studying asymptotic, so we're always assuming the system size is very big, so poly log n is also very big.
Well,
Yes,
Like n,
you're,
if n is like the security parameter of your randomness, then log n is not that big. Or am I missing?
security parameter if you're in log n is not that big.
Okay, that's matter, sorry.
No, it's a good, I think you might be getting to this. Basically, we, yeah, so we can assume we have very good existing constructions of PRUs which have sub-exponential security in the number of qubits. So they're secure against any sub-exponential time
The
algorithm.
PRUs
Yeah,
of
yeah.
size linear in n, in the security parameter.
Size linear. No, so sub-exponential, so we take sub-exponential of poly log n. And this is secure, this is bigger than any poly n function. Basically because of the polylog. If this was just a log, it would be linear, like you just said. But if you take just a polylog, so like log squared or log cubed, then it's greater than any polynomial. Just barely, but it is greater than any polynomial. And if you make these patches a little bigger, like if you made them scale with some small polynomial in n or something, then this would become a better security. Does that answer the question? Kind of? Okay, okay. I can try better afterwards. Yeah.
What she says implies that you cannot reduce the polylog n to log n, because then polytime people really just estimate the whole.
Yes. Yes. So, and we can actually, so there's a recent paper on learning shallow quantum circuits by Yunchao Liu and Robert Huang. And they show that you can learn any log depth circuit in polynomial time. And that basically proves that, yeah, you cannot get PRUs from log depth circuits. And then we show you can get them from polylog depth circuits. So the poly is, greater than 1. The degree.
For instance, log n squared, can you tolerate this?
It's a good question. In the end, we started to get down to the precise polynomials, but you have to go back kind of deep into cryptography literature on how people realize these particular pseudo-random functions that get called in the PFC construction. And people are very loose with their constants in these papers. So we don't actually know the precise degree of the polynomial, or at least I don't. Yeah, but it certainly has to be larger than 1.
you have some bounds on it? Less than 10?
Again, we don't, but for lack of trying.
Okay,
We
yeah.
are not, yeah.
There is a number out there, just don't know.
Yeah, it would be good to know it, and, but yeah, I don't know. Okay, so those are our results. Now I'll tell you how we prove them. And our proof is relatively simple. We kind of prove both of these theorems brick by brick in a way. So in particular, we prove this simpler lemma, and this lemma is the foundation of both of our results on designs and PRUs. And the lemma is basically showing that we can always glue 2 random unitaries that overlap on only a small number of qubits into a bigger random unitary that acts on the union of both of the small ones. So it goes as follows. Let V be the product of a unitary on AB. So that's this blue unitary here, and a different random unitary on BC. That's this green random unitary. And we assume that both UAB and UBC are drawn from K designs with some error epsilon prime on the subsystems that they act on. And then we show that their product B is a 2 epsilon prime plus K squared over 2 to the NB, approximate K design on all of the qubits. So just to explain this error, the 2 epsilon prime just comes from adding the error of the first K design and the second K design. And then we get some additional error from gluing them together from the fact that they only overlap on a small number of qubits. But that error we show is suppressed exponentially in the number of qubits in this overlap. So it goes as k squared divided by 2 to the number of qubits they overlap on. So by taking the overlap to just be logarithmic in k and epsilon, we can get a design with basically just as good of error. And so I'll tell you in detail how we prove this in a bit, but then I'll just show how we use this to prove our two main theorems. Yeah.
Yes, and what if, let's say, the k of the two units is different, let's say if k and k prime, would it still work?
I would only know how to get the minimum.
You only,
Yeah, that's all I would know. Yeah. Okay, so to get theorem 1 from this is extremely immediate. We just apply the lemma n times. So the first time we glue the first unitary with the second unitary. So this takes 2 unitaries that each act on 1 patch and gets a unitary that acts on 1.5 patches. And then we take that combined unitary and apply the gluing lemma to it in the third unitary. And this gets a random unitary acting on 2 patches. And then we take that big conglomerate unitary and apply it, we glue it to the next unitary, and so on. And in the end, we get an error that's like n times the epsilon we put in. So that's why we required the epsilon we put in to be like 1 over n. Plus this k squared over 2 to the nb times n, because we applied the gluing lemma n times. And so in the end, the error is like n k squared over 2 to the nb. And so we just need to take nb to be greater than log nk.
why don't you use two different epsilons here? Because the epsilon adds, right, if you glue.
Yeah.
The next one you add is like still a smaller epsilon than before.
Yeah, you can probably improve these bounds by, oh, no, but the overlap is always the same. Does this make sense?
Yeah, but the part you've already glued like before,
Yeah.
that one becomes bigger and bigger, but then
Yeah.
the epsilon grows there.
Oh, yes. We do that in our results. So we would do like epsilon 1 and epsilon 2
I see.
we put in, and we get epsilon 1 plus epsilon 2 plus this. Yeah,
I see.
maybe I should, still working on how to put it in a simpler form for the slide.
Yeah.
There's also, I should say, there's some subleading terms, like terms that are suppressed in higher powers of 2 to the nb that we neglect in this expression, but not in our paper. But yeah, we do it exactly how you said. And just a brief remark, one of the nice things about proving this kind of brick by brick is it's easily adaptable to other like 2D circuits. So this is a top-down view of some like 2-layer brickwork circuit in 2D. And applying the same gluing lemma, you can show that this gives you designs. For PRUs, the proof is actually super simple once we have the design proof. So the first step is just the definition of a PRU. So if we assume each of these small unitaries is drawn from our PRU, that means it's indistinguishable computationally from a small Haar random unitary. So then we just need to analyze this 2-layer circuit where each small unitary is Haar random. And then if we look at this gluing lemma, this is basically the gluing lemma where k can be any value, like goes up to infinity, and epsilon prime is 0. And that means we get out a design for every k with error k squared over 2 to the nb. And so if we take nb to be polylog n, then 2 to the nb is greater than any polynomial. And that means this is a very good design for any polynomial k. So this error will be like poly n, if k is some polynomial, divided by something that's bigger than any polynomial. So the error is smaller than any polynomial. So the 2-layer Haar ensemble is a design for any polynomial k and any 1 over polynomial epsilon. And by definition of designs, that is indistinguishable from a Haar unitary in any polynomial time quantum experiment. So the PRU proof really just follows essentially from the design proof.
Does this lemma depend on how you look at these ABCs? Because now you explained in a way that ABCs are aligned in one line, but
Yeah.
what if you have like stitches of ABCs? Let's say you have like regions of A and B, some of them are B, but it's like surrounded by ABC. Does this approximation get improved by that?
think. Um. The approximation, because we're not really assuming anything about the underlying geometry. It just depends on the overlap.
Exactly. Because I was thinking that if that's possible, then we can also make log depth. Or, but if it doesn't rely on geometry, then you think this is the best you can do, right?
This is the best. The reason you can't like apply this again to get log is because of the error. So it's because, okay, it's clearest to see here maybe. We need to put in epsilon over n approximate designs. So before we applied our trick, our designs had depth n plus log 1 over epsilon. Now we apply this trick and we get designs with depth log n plus log n over epsilon. So this term gets way better. This term gets a little bit worse by a log n factor because we had to demand that epsilon is 1 over n. If we tried to apply this again, this term will go to log, it'll get much smaller, but this term will still be log n. So we don't improve anymore if we try to just recurse this trick. Yeah.
Why do you even have two terms inside the parentheses? Isn't the second one just absorbed by the first?
Yeah, that's true. That's true. I just wrote it this way to try to be more clear because this is the number of qubits and this is the error. But yeah, the second term is absorbed first. Yeah, it's a good idea. I tried it too. And you can do a funny thing where if you instantiate these as Haar unitaries, which have exponential depth, you immediately get out something with polynomial depth, and then you can apply it again and get log depth. So it's like an independent way of getting log depth designs that doesn't require, but the T dependence is much worse. So it's better to use Jonas's result. Okay, so now this will be the slightly more technical part of the talk, but really not that bad, of how we prove this gluing lemma. And so, yeah, what we use at the root of it is this very standard and well-known connection between averages over random unitaries and the permutation operators. So if we look at this, it's called the twirl of a random unitary. So we take some state rho acting on k copies of the system, maybe some ancilla qubits as well, but say k copies of the system. And we apply the unitary k times in parallel. So we apply, k of u to the ket of rho and u dagger to the pro. And then we take the expectation value over u. And for now, just trust me, this is kind of the right object to study for bounding whether something is or is not a unitary design. And so if u is Haar random, there's a very well-known expression for this average, which involves a sum over operators sigma and tau. And these sigma and tau are permutation operators on the k copies. So they take, each of the copies that we start on and they just shuffle them around. They permute them with other copies of the system. So I can draw it kind of like this, where each of these lines represents like the entire Hilbert space of a copy of my system. I'm moving like the entire Hilbert space of the first copy. I'm swapping it with that of the second copy, doing something different on the third, fourth, and fifth here. And so the reason why these permutation operators are relevant for the study of random unitaries is because they're the only objects that commute with the k-fold tensor product of a random unitary. So if I apply a bunch of u's at the beginning here, that's the same as applying the same k copies of u at the end. I can kind of slide each u along each of these permutations. And it turns out that the permutations are the only operators that commute with all the unitaries. And so when you average rho over u, basically every part of rho that does not overlap a permutation averages to 0. And the parts that do overlap the permutations just commute through the u and u dagger and stay preserved. And this formula is just a way of taking rho and projecting it onto the subspace of operators spanned by the permutations. So what I do, I first take the inner product of rho with some permutation sigma. There's then this funky object called the Weingarten function, I'll describe in a bit. And then I get out a permutation tau. And this Weingarten function is a function of the permutation sigma and tau. And it's actually a very simple function. So it's the inverse of the overlap matrix or Gram matrix of the permutations. So the overlap of two permutations is just their trace product. And I can view this as a k factorial by k factorial matrix, where the matrix elements are indexed by the permutations. And the Weingarten matrix is the inverse of that k factorial by k factorial matrix. And its elements are what appear top. Yeah.
Are you going to run into trouble when this thing is not invertible? Because sometimes it isn't, right, if k is large enough.
Yeah. So we're always going to assume that, yeah, so we need k squared is less than the Hilbert space dimension of each small random unitary.
Yeah, which is log of n-ish.
Yes,
Yeah.
yes. So, yeah, so this immediately, okay, this comes back to your question earlier. This immediately only works for k squared less than exponential of the size of the patch, which if we take the patch to be log is linear in n. If we wanted higher k, we could increase the size of the patch. But yeah. So all of our, all of the theorems, I didn't write it, but they rely on k squared as being less than this Hilbert space dimension. And it's pretty easy to argue why the matrix inverse appears in this expression. It's basically you're projecting something onto a non-orthogonal basis. And you have to kind of take into account that basis vectors, the permutations are not orthogonal in order to get the right formula for this projection. It's pretty easy to derive. Okay, so how do we get the gluing lemma from this? So I'll give you a one slide proof. And it's actually, we've simplified it since our original paper. So this is the even simpler version. So the key fact is that these permutation operators, when the size of the Hilbert space gets relatively large, they become approximately orthogonal. The trace of sigma with tau inverse is 0 unless sigma equals tau. A very good approximation. So this appears in lots of work. It's very nicely formalized in a recent work by Aram Hara. And what this means is that this matrix G sigma tau, which is the overlap matrix, is approximately a delta function. It's approximately the identity matrix when the Hilbert space of each unitary is much bigger than k squared. And similarly, the inverse of G sigma tau, so this Weingarten function, is also approximately the delta function, the identity matrix. And so the first thing to note, so this is something we show in our work, is that this implies a much simpler form for the Haar average. So namely, we can replace this Weingarten function we had before with just the identity matrix, which sets sigma equal to tau. And okay, this is kind of obvious if you just look at the squiggly signs, but we show that this approximation holds to very good approximation. So it holds to within small relative error, where this relative error I got earlier. So this is very nice. It gives a formula that's much easier to analyze. And then once we have this formula, the gluing lemma follows pretty immediately. So this is the object we start with that we're interested in. And let's just take the average over the first unitary and over the second. So we can apply this formula to take the average. And say this introduces some sigma corresponding to the first blue unitary and some sigma tilde corresponding to the second, the green unitary. So the expression I get out looks something like this. Basically, I take the inner product of rho with sigma on AB and sigma tilde on C. And my output is like sigma on A and sigma tilde on BC. And crucially, there's one term in the middle, which is where the first unitary and the second unitary link, so on B. And that term takes the output of the first, which is sigma, and it feeds it into the second. So it traces it with sigma tilde. And now from above, let's just apply that equality again. This is approximately a delta function. So this sets sigma equals to sigma tilde to within very good approximation. And if you just do that, you get that all of these sigmas are the same, and you get out the formula for the hard twirl on all cupids. So that's that.
I guess almost all of the actual work is in the squiggly lines, right?
Yeah, even the squiggly lines are not so bad. It does involve a kind of lemma on how you relate relative to additive error. And then I have a slide, backup slides for it, but yeah, you basically, there's some lemma that relates relative to additive error, and then you just apply the triangle inequality. And then you can get the squiggly lines fairly easily using Arrow's result. And even Arrow's result, you can prove it in my path. It's very short. Yeah, just once these permutations are orthogonal, everything becomes very simple. So I'm happy to go into more details, but for now, I'll just kind of briefly mention a few applications of the result. Yeah.
Guys, one question, I'll
Yeah.
add to the NB, on the previous slide, when you went from, in one of the squiggly lines, there was like a N plus NB.
Yeah, okay, yeah, there's little errors popping out in each of these squiggly lines. So in this one, we have an error. So this first middle formula has an error that's like 1 over the Hilbert space dimension to which we're applying this. So we first get an error that's suppressed in the size of AB.
Yeah.
And an error that's suppressed in BC. And then going from that, the second to last expression to the last, we get an error that's like 1 over the size of B. So yeah, there's like, and then we get like a fourth error where we apply this last squiggly. So there's 4 errors, but the dominant one is, it's the one that we applied just to B, and that's like k squared over 2 to the NB. The other ones are like k squared over 2 to the NBC or something. Okay, so applications. So there are a few cases where it's very nice that you can get random unitaries in very low depth. So I'll list a few and hopefully we can come up with more in the future. We have a few more in our paper too. A very obvious one is for classical shadows. So as I mentioned, classical shadows is this protocol for fidelity estimation. And the original protocol requires a random Clifford. And since then, you know, a random Clifford is not too bad in the grand scheme of things, but it's kind of not great for immediate experiments right now. You know, it requires linear depth, say in 1D, which takes a lot of gates to implement. So it's hard to implement that to very high fidelity on lots of qubits. And so there have been several very interesting follow-up works to the original classical shadows paper, proposing that maybe you can get away with much, much lower depth. And our result basically confirms this. So we just immediately show that log depth random Clifford circuits are just as good as truly random Cliffords for classical shadows. Hopefully, you know, with some backup of the envelope estimates, you can estimate that classical shadows could be implemented to good fidelity on roughly 40 to 50 qubits with current noise rates. And just to remark this, in applying our results to classical shadow tomography, we actually really rely on the fact that we get relative error, this very strong notion of error for unitary designs. The second two kind of interesting applications are to learning. So this question of what properties are easy versus hard to learn. And the first one I'll mention is a case where it's really important that we now have very low depth random circuits. And we can use this to show that, at least in certain regimes, recognizing the phase of matter of an unknown quantum state is computationally hard. So specifically, say you give me some many body quantum state on lots of qubits, and you tell me that it has either trivial order or topological order. So topological order is like, for example, the toric code state. But more broadly, a very wide class of phase of matter that lots of people have been interested in the last 3 decades. So what we can show is that if you know no details, no further details about the state, recognizing whether it has trivial order or topological order is quantum computationally hard, at least in certain regimes. And the way we show this is very simple. We use a defining property of topological order, which is that the topological order of a state is invariant under any low depth quantum circuit. So then we take a product state with trivial order and apply a low depth random circuit to it. This produces a random ensemble of states with trivial order. And we take a toric code state, which has topological order. We apply a random low depth circuit to it and get an ensemble of random states with topological order. And because these random circuits are pseudo-random unitaries using our construction, this produces two pseudo-random ensembles of states. So neither this ensemble nor this ensemble can be distinguished from a Haar random state. And so by the triangle inequality, these ensembles can also not be distinguished from each other. And so we cannot recognize whether the state has topological order. Yeah, I do want to comment. I mean, in practice, people have found that recognizing the topological order of states is very hard, and there's lots of work on devising smart strategies for it. You can see our results as somewhat confirming this, saying it's impossible. But I do want to emphasize this is a worst case statement. So it applies to this specific ensemble of random states that we have constructed using our circuit. And the states that we find in the real world, which are ground states of some local Hamiltonians, might have some simpler structures, or we might have some prior knowledge about order parameters in those states that allow this to be efficient or more efficient. So I think it's still an open question whether the topologically ordered phases we find in the real world are hard or easy to identify. My guess actually would be easy, but I don't know for sure.
Sorry, but can one just interpret this result as just argument for the fact that those definitions of topological orders are not so good? Because from physics perspective, you have those systems that have specific features and you just scramble them by objects.
I think the right
They do, maybe.
I think the right perspective is, yeah, from a quantum information viewpoint, these are very good definitions because all these states have the same kind of patterns of entanglement that characterize topological order. But it just happens that the states we find in the real world are ground states of local Hamiltonians. And even if they have some very large entanglement and high correlation length, the fact that they're obtained from local Hamiltonians and there's some physics of the renormalization group going on, it means that in the end, they might be much simpler than a truly random state. So I think it's like a good definition from a quantum information viewpoint, but it's missing the fact that just the states we see in the real world are much less random than you might naively expect.
I'm sorry to press you on this, but you mentioned the entanglement pattern,
Yeah,
right?
yeah.
But when you scramble the
Yeah,
states, like many features of entanglement just kind of the same, right?
Yeah, but the features that topological order cares about are maintained under any low depth circuit. Like you can show if you knew the circuit, there's some order parameter you can measure to just verify whether the state has topological order. But if you don't know, it's hard to guess. Laura?
Just gonna comment or like, I guess relatedly, like, it seems like you can only really talk about this like asymptotically because this result is asymptotic.
Yeah.
But maybe in the real world, like there's some like characteristic timescale you care about. So I wonder if that's relevant as well.
That's possible. That's possible. I mean, I think if you, I think what our results somewhat is saying is like any strategy, any very generic strategy to learn topological order will blow up exponentially in the depth or the correlation length of that state. So in the real world, maybe your correlation length is 3 or 4, and that's not that bad. That's how I view it.
Yeah.
And for example, in this like learning shallow circuit paper by Yunchao and Robert, they prove the opposite. They prove that if the correlation length is less than log, then they can learn it.
Okay.
So it's a very similar transition. Yeah, but the question would be, can you exploit some property of states in the real world to design a learning algorithm that does not scale exponentially in the correlation length of the state? I think that's an open question. Okay, sorry, I know I'm running over time. This is my last, okay. This is maybe the last application I wanted to mention, which is maybe a little unexpected. So it's the power of time reversal in learning about quantum processes. So as I've discussed, our work shows that no experiment querying a unitary U can distinguish whether U came from a low depth or very high depth circuit. But our construction actually just immediately breaks down if you consider experiments that query both U and its time reverse, U dagger. And there's like a very simple light cone experiment you can do. You just apply U, flip a qubit, apply U dagger, and you can tell whether the unitary is low or high depth. And so this is kind of a corollary of our results, is a proof that quantum experiments with access to time reversal can probe properties of dynamics that are exponentially hard to detect without time reversal. And this was kind of proven in a slightly weaker form in earlier works of mine with Google and Jordan Kotler, but it's proven in a much stronger degree in this work. And one of the nice things about this separation is it holds for like lots of very physically motivated learning tasks. Like we already saw, like learning whether a circuit had low or high depth. It's a fairly physical task. And we can also extend it to things like detecting whether some time evolution arose from only short range interactions, say in 1D or 2D, versus a combination of short and long range interactions. Again, both of these kind of locally scramble information, so they become very hard to distinguish from hard unitaries if you just have U. But if you have U dagger, you can measure light cones. And light cones behave very differently in short range interacting systems from long range interacting systems. So you can pretty easily distinguish these. Yeah, I'd be curious if people have any other interesting applications or ideas for this result. It was not really intended by our work, but it came about as a consequence. Okay, so that's all. Just to summarize, shallow quantum dynamics can very rapidly become indistinguishable from deep hard random unitaries. And just like if you take anything away with you, like fundamentally, this is just enabled by the abundance of non-commuting observables in quantum systems, which allows circuits to rapidly hide information into observables that are very hard to guess and extract information from if you don't know the circuit. In the spirit of this workshop, I tried to list a bunch of open questions that I'm interested in, or at least, yeah, so a few of them I'm working on, sparked by this topic. The first, there's kind of several smaller mathematical questions that remain open. Like, for example, our designs have depth k times log n. And we can show that the dependence on k and n individually is optimal. But we can only show that k plus log n when you combine them is optimal. So I actually don't know which of these is correct. Another question is, can you achieve the same results with just local random breakwork circuits? So without this kind of patch by patch construction. And I was told yesterday that you can, at least for 2 designs. So that's nice. Some other kind of slightly more different directions. So I mentioned at the end that time reversal experiments break our construction, and they break like our existing notions of approximation error for unitary designs. This initially kind of surprised and upset me a little bit because I cared a lot about designs in the context of information scrambling. Like this is a topic physicists have studied a lot. And it was a little disappointing to learn that even this extraordinarily good notion of error, the relative error, simply does not capture many of the applications of random unitaries in information scrambling and quantum gravity. So something we're currently working on is just very straightforwardly writing down a new notion of approximation error for designs and proving, you know, some basic results. Can we get designs in linear or log depth in that setting? And in general, these require larger depths. They require the depths that are intuitive to you from light cone arguments. But proving this has actually been quite tricky, especially to get log depth in all-to-all circuits. So that's something ongoing. Another kind of extension of designs I thought was interesting was to systems with Hamiltonians. So in physics, like lots of the applications of designs we care about are trying to understand properties of systems in the real world. But in the real world, systems normally evolve under some time-independent Hamiltonian. And they don't approach a random state, they approach some random pure state from a thermal ensemble. And I think it would be nice and fairly natural to somehow extend the ideas of designs and pseudo-random unitaries to this context. And maybe just to motivate this, there's already a very well-known source of randomness that which we use to characterize Hamiltonian systems called the eigenstate thermalization hypothesis. And my feeling, maybe this is just a guess, but I think it might be useful to kind of unify these into one hypothesis of how Hamiltonians look like random matrices. Okay, I think that would be cool. Maybe looking farther ahead, not really related particularly to this work. So our work shows that circuits converge to Haar random behavior pretty quickly. And Haar random unitaries, hopefully I convinced you at the beginning, are useful and interesting for many purposes. But at the same time, from like a physics perspective, it's also kind of the end of the road. Once you hit Haar random behavior, nothing else is changing in time. And I think there are lots of kind of interesting works that investigate not when you reach Haar random behavior, but how you reach it. And I think this question is actually much more open. And there's lots of work proposing that maybe this is a nice arena to study quantum advantage in simulating many body dynamics. Like maybe how you reach Haar random behavior is complex or not, but at least maybe we can make some concrete statements in these different contexts. So that's all. Thank you all for the questions and your time.